So briefly speaking, DPGN is a tool to generate a deep potential model so that you can run your molecular dynamics. And it uses the so-called active learning approach or concurrent learning approach to determine which configurations you need to label to perform the first principles calculations. And okay. And the advantage of using DPGN is that it can minimize the number of first principles calculations you need to do so that you save a lot of computational effort, and you will very efficiently explore the configurational space so that you sample enough configurations. And before explaining in detail how DPGN works, I want you to start your DPGN task, as it may take 1.5 hours to finish this training. So now you can go to the DPGN folder and go to the folder DPGN hands-on restart, and you activate the Kanda environment deepfd, and you just copy paste this command, no hub DPGN run this command, and run it and execute it. I'm putting the command you need to run in the chat, and now I will share my screen to show how to do this. So this is my virtual machine, and I go to 6 DPGN, and I have a, and I go to DPGN hands-on restart, and and I activate deepmd, and I copy paste this command, and I execute it. So I'm giving you half a minute to do it. Are you okay with this? Do you have any questions? Very good. Are you successful in executing this command?
Yeah.
Okay, so nothing wrong happens, right? You're able to run this test. Okay, perfect. And this is the only command you need to run this afternoon. So if you're successfully if you're successful in running this command, then there's nothing you need to run this afternoon. And in the rest of this afternoon, we will explain in detail how DPGN works and how to understand the large amount of files in the large number of files in the folder. And also, after the test finishes, we will see in detail what the generated files are, and how to understand the logics of the files. Okay, so let the machine run the test, and yeah, and let's start our explanation. Okay, I will start my screen again. Share my screen. Okay, so I'll first explain a little bit how uh, 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 what these two folders are. So I'm providing you with two folders in this 6DPGN folder, and one is called DPGN hands-on raw, and the other is called DPGN hands-on restart. And in these in the first folder, there is a task. There is a DPGN task that runs from scratch, so we call it raw. And there's no model trained. You need to train everything from the start. If you want to run this test, this will take 2.5 hours. And I trained the model for the first stage, and I saved the model so that you can start from the middle and do the following things. And we are using this strategy in the workshop. So the files are in DPGN hands-on restart. The only difference between these two directories is DPGN hands-on restart contains some model that has been trained for a while, so that it will save you some time in this workshop, since we will not have enough time to let it run for the whole process. So next, I will briefly introduce how DPGN works, the logic of DPGN. Let me start. Yeah, the basics of DPGN. Let me first introduce a little bit what are included in the DPGN hands-on raw folder. Okay. If you open this folder, you will see a folder called methane.init.data and two JSON scripts, and one script that is the command that runs this DPGN task. This task will generate a deep potential model that is a force field for a methane molecule. So we prepared a system of 5 atoms that is a methane for you. And we have some initial data so that you can train a small deep potential model with this small set of initial data, and then continue the DPGN process. So in DPGN, we first generate some configurations of the system, and then we do the first principles calculations so that we have some training data, and we train the model with deep MDKit for a while. Actually, we will train 4 models at the same time, and the parameters of the 4 models will be totally the same. The only difference will be we will using different random seeds in training the four models, so that we will have four different models. Let me show you how the initial data looks like. So this is the initial data, and if we open one, for example, we open energy, we can find that there's some energies, and we have 200 initial data. So we train four DeepMD, we train four deep potential models with DeepMD using the same set of data, which is composed of 200 configurations. Yeah, so we have 200 lines in this cohort.raw. So we have 200 configurations in the initial data, and also you can check that there are 15 columns in this file. This means you have 5 atoms, and so the first stage of the DPGen task will be training, and we will train a deep potential model with DeepMD kit. We will train 4 models, and in DPGen we use some labels to represent different stages of the process. And stage 0 means is called make train. That means generate the training input script of DeepMD kit, which I just mentioned. And stage 1 is run the training. So we train the 4 models in this stage. And the stage 2 is called post-train, so that we do some post-processing for the trained models. We copy paste them to the appropriate directories, and we also clear some directories so that in the training process. After training, we will compute the model deviations of the 4 models trained in the last stage. So the second part of a DPGen iteration is called model dev. It's the shortcut of model deviation, and it also consists of 3 stages: make, run, and post. So stage 3 of a DPGen iteration is called make model deviation. That is, in this step, we generate some LAMPS input scripts, and also we make the correct directories to run the LAMPS tasks. And then stage 4 is called run model deviation. The things we do in this stage is that with the 4 models, we run 4 molecular dynamics trajectories of several steps. For example, with 1,000 steps, and we can after we when we generated the 4 trajectories, we will have 4 sets of energies and forces with the same set of trajectories, with the same set of coordinates. So we can compute the standard deviations of the 4 force values for each configuration, and we will determine which coordinates. We will determine which configurations we will determine which configurations to be labeled. The logic is that if the four models can predict the same energy and force for a configuration, then that means this model can predict very well for this configuration, and we don't need further training data on this configuration to be added into the data set. However, if the four models provide very different predictions for a specific configuration, this means that we cannot, the model cannot work very well for this specific configuration. So we will label this configuration. That means we will compute the energies, the energy, the force of this configuration, and add the label of this configuration into the data set, and then train the model again, so that the model has the ability to make predictions on this configuration. However, if the difference between the four predictions is too high, that means the configuration is somewhat unphysical, and we will not label this configuration. So we have two parameters which are the threshold of the model deviation. If the model deviation is higher than a lower limit and lower than a higher limit, then we think that this configuration is a candidate to be labeled. And if the model deviation is lower than a lower limit, then we think this configuration is good. And if the model deviation is higher than a higher limit, then this configuration, we think that it has failed. Okay, so I just explained how the principles of, I just explained the principles of selecting candidates for the configurations to be labeled. And then in stage 5, post model deviation, we record the we record which configurations are good candidate or failed, and then make clean the directory, and also copy paste the candidate into the appropriate directory, so that we can do the next step. And in the next step, we want to label the candidates so that we can add them into the training data set. So the next step is called FP. FP stands for first principles. It also consists of 3 stages: make FP, run FP, and post FP. Make FP generates some first principles calculations input scripts. For example, the input script of Quantum Espresso or VASP, and run FP runs these first principle tasks, and post FP post FP as these configurations and their values and forces just calculated from first principles into the training data set, and do the necessary format transforming, and so that DeepMD kit can use these data to train the model. The 9 stages, 0 to 8, consist of an iteration in DPGen. And after one sorry, there is someone saying in chat. Which first principle codes are supported by DPGN? That's a very good question. So in this workshop, of course, we use Quantum Espresso, and we also discussed a lot about how to use Quantum Espresso yesterday. And if we check the document of DPGN, if we check the document of DPGN, there is a parameter called init fp style. This parameter defines the first principle software to be used in this DPGN task. And in my knowledge, VASP, Quantum Espresso, CP2K, and Abacus are all supported by DPGN. And this may not be the complete list. So it depends on which software you want to use, but both VASP and Quantum Espresso are supported. Okay, and let me explain further about the iterations in DPGN. I have already explained the 9 stages that consist of an iteration. Then after one iteration, you will have you will know how many configurations in the model DV step are good, are regarded as good, and how many configurations are regarded as candidate, and how many configurations are regarded as failed. So you have a number called successful rate. For example, if I have 90 good configurations out of 100, then my successful rate is good. My successful rate is 90%. And if we achieve a satisfactory successful rate, then we can finish the DPGN task so that we can claim that we will succeed in most of the prediction jobs. However, if we don't achieve a satisfactory successful rate, then we will enter the next iteration, that is train the model and calculate the model deviation, and also do the first principles calculations to label the data. And then we have the successful rate of this iteration to determine whether to enter the next iteration. So we can have many iterations until we have a model that is accurate enough. Also, I want to mention that this model deviation step is also called exploring the configuration space, so that we can, this is because we are running molecular dynamics, so that we are generating some data in the configuration space, and see if this part of the configuration space has been learned by the model. So this step is also called exploring the configuration space. Okay. So this is typical, like how a DPGN task works. The question is there a parameter for the successful rate to determine if DPGN will enter the next iteration? Okay, typically people will use 95%, and also in the input script, you can determine how many iterations you will use. For example, in this task, we are using in this task we are running in the workshop. We are setting 2 iterations. I will let you see the parameter.json. I will explain this script in detail, but let's see. So in this part, you will see model deviation jobs, and actually it defines how it defines in each iteration how the model deviation step works. So in the following, we can see in the first in the following, so in the first iteration, it will the model deviation job will be controlled by these parameters, and in the second iteration, the model deviation job will be controlled by these parameters, and both these 2 jobs has the temperature of 50 Kelvin and a pressure of 1 bar, and they are both MBT molecular dynamics jobs. The only difference is that in the first iteration, it will run for 1,000 steps, and in the second iteration, you will run 3,000 steps, and we can check further the files generated to understand this part. Okay. After understanding the logic, how an iteration in DPGN works, and how DPGN is composed by many iterations, let's go into the details of each iteration. So in each iteration, we will first do training, and then we will do model deviation, and then we will do first principles. So let's see the files. So I'm entering a folder where an iteration has completed. So we have 3 large stages: train, model DV, and FP. And we will see what is included in each folder. We first enter 00.train, and you will see that there are 4 folders, 000, 001, 002, and 003. These 4 folders are actually the training directories of 4 models. So we enter 000, and you will see that at least there is an input script for DeepMD training. So this is a DeepMD training script, and yeah, these are the training parameters, and the stop batch is set to be 40,000, so that we will train it for 40,000 steps, and the model trained is here, frozen model.pb. This, and we can also see the learning curve of this training. We trained it for 40,000 steps, and you can see that the root mean squared error decays, and and 001, 002, and 003 are all the training folders, the training directories of deep potential models. So we have 4 models trained in this step. So this is the training stage. So this is the training stage, and I just explained the things. Also, if you want to visualize the learning curve, we can use GNU plot to. You can use GNU plot to visualize the learning curve. Remember to add a -h when you want to use the plot. GNU plot, and we can plot the learning curve. Yeah, you can see a learning curve, and the root mean squared error decays very fast. And if we set the scale, the y-axis to be log, we will see it more clearly. Yeah, you can see a log decay of the the root mean squared error. So this is the learning curve for the training, and we train the 4 models. And the difference between the 4 models can also be observed. So we use diff to see the differences. You can see that the only difference are the C's, and there's nothing else that is different. Okay. Now let's step forward to see the model deviation stage. So we train and see model deviations. Actually, in the DPGN hands-on raw folder on GitHub, there's no these 2 folders, but after I run it for some steps, then we will generate these 2 folders. So let's see it. In the restart folder, I just did this stage 00.train for you, and afterwards, it is the other things are being done right now on your virtual machines. So in this model deviation folder, you can see that there are 4 models that are linked from the training folder. And then there are several tasks. There are 10 tasks. I see a question in chat. For the initial random structures, will these be optimized or just the AIMD will be performed? I think neither. Actually, we perturb some optimized structure to generate a set of structures, and we perform single point of first principles calculations for those structures so that we have a set of training data, and we use this set of training data to train the model. And we actually don't need the AIMD. We just do several separate DFT calculations. Did this answer your question? Yes. Okay. Let me continue. So let's see these 10 tasks. So each task is a LAMP's job. So if we see the input script of a task, you can see that it's an input script of LAMPs, and it uses the 4 models, and inside this, it uses the average force of the forces predicted by the 4 models to drive the simulation. And after the configuration is generated, after the it will be written, several configurations will be written out, and then the 4 models are used to predict the energy and forces of those configurations, and so that model deviation out, so that the model deviations are written here. And we are using the model deviations of force to determine the candidates. And yeah, just that you see how model deviation looks like and how they are calculated. Okay, so okay, let's move further. So from that, you can see how model deviations are calculated, and then we see we go to the folder 02.fp to see how DPGN performs the first principle tests. This step will use the configurations chosen as the candidates to perform the DFT calculations. You will see three text files. They are called candidate, rest accurate, and rest failed. So let's open them. Let's open candidate. We will see that there are 34 lines, and each line records the index of a configuration in the model deviation step. And you can also see rest accurate. It has 960 and 76 lines. We can see rest failed and no configuration failed. So all the configurations explored are physical. So in total, there are 1,000 configurations and 34 inside them failed. Since we set the maximum number of first principle tasks to be 30, we have 30 first principle tasks which calculate the energies and forces of 30 structures selected from the 34 candidates. So we have 30 task folders, and each task folder is a folder of one single quantum espresso self-consistent task. That's the input. This is the input script of quantum espresso, which was explained by Zach yesterday, and it performs the SCF calculation using quantum espresso. So this is the first principles stage. And the three stages. Actually, that's 9 small stages, but they are actually 3 large stages. The 3 large stages consist of an iteration. What's happening? Here's some questions. Question: the command does not run, no hub, ignoring input hub, fail to run DPGN, no such file directory. Did you do can't activate deepmd? Yes. Oh, for this question, if you want to know that whether your installation of DPGN is successful, you can use dpgn-h. Yeah, this is someone. There is someone talking about this. So if you run dpgn-h, you will see the help information of dpgn, and it will tell you the usage. dpgn, it has some modules. It can generate the initial data for several kinds of systems, and also it can run, we use the run to run that dpgen task. Okay, got it. Okay. Also, you can use dp-h to check the help information of dp, and there are also many useful modules that are written here. And lmp-h is also helpful, in fact. Okay, just to mention that you can check the installation so that you can make sure you have the correct environment to run the program. Okay, let's go further. Now I will go to a folder where I finished the task that you are running and see what is included in this folder to further explain how dpgen works. So in this folder, you will generate an out.log file. This file tells you the log of the dpgen task, which jobs it submits, and whether they are successful or not. So we can read this this file. The first iteration is iter 000, and we actually start from task 4. I think we should start from task 3, 0, 1, 2, task 3. Anyway, I think it should start from task 3, but yeah, task 4 is the run model deviation. So you're running some molecular dynamics jobs, and task 5, and after that, after you run some molecular dynamics, you can calculate the model deviations, and you can see that the accurate ratio or the success rate I just mentioned is 98.22%. So that you have you have 18 configurations to be labeled, and you submit 18 first principles tasks in the next step. So that is task 7, task 8, and then you finish the first iteration and you enter the next iteration. In this iteration, the difference in training is that you have 18 more training data, so that you add these training data into your data set, and you train your model at task 1, the post-processing, and make model DV and run model deviations, so that you run the molecular dynamics with the potential with the model you have just trained in task 1. And you also calculate the model deviation. And in this step, the accurate ratio becomes 95%. And you have 30 tasks, that 30 first principles tasks that should be done. And after that, the first principles tasks, you finish the second iteration, the iteration that is labeled 1, the second iteration. And since we just set 2 iterations in the param.json file, we have finished all the iterations. And the next thing to do is to collect all the labeled data